Hi, Victoria. How are you?
I'm well, thank you, Katarina. How are you?
Good, good. Nice to see you.
Yes, likewise. This should be such an interesting discussion tonight.
Yes, I agree. I'm really looking forward to it, and I uploaded the PDF onto our Google Drive so everyone has access. And yeah, great. I was a little bit late. I had to do some things before starting the room. So, but it's fine.
Yep. Know about that. They're still doing the things.
Exactly. Let me put the lab website in the chat.
Now the room looks so pretty.
There it is. Perfect. Okay. Yeah. Then I'm really happy that our little team is here. So much fun. The discussion earlier today was really amazing too. But it's so early for you. But
Well, I'm
the
driving to school, so I really couldn't. I have to focus. I mean, sometimes
yeah.
I could come in PTR form, but I would just want to come and listen and talk. So I have to just focus.
Yeah. Yeah, I understand. He's from Norway, but he's currently in Iceland. Um, yeah, it was really interesting. It was a great discussion. I love the variety of topics that we have. It keeps it always interesting.
Yes, except it's so hard to miss them. I feel like, oh, why does this one have to be right when I'm teaching? But all of them are that way. We have such, yeah, we have kind of something for everyone, no matter what your background or personal interest. I feel like.
Yep.
Um,
Oh, hi,
there's-
Lucas. How are you?
Hello. Doing well. How are you?
Good, good. Thank you for coming.
Absolutely.
oh, there you are.
Thanks
We
for the
Sorry. Hello. Sometimes my app doesn't show who's in the room. It's kind of mysterious. I hear a mysterious voice. So sorry.
oh
okay.
Hello.
Nice to meet you.
Likewise.
yeah, Lucas, we I'm very happy that you made it because you had you jumped in very short term, so it's really great of you to come today and do this. It's really nice of you.
Yeah. Hopefully I'm prepared well enough, but I think it should be
Oh well, who
pretty
else should
straightforward.
know more about your project? I
Right.
mean,
Right.
um,
Yeah. No. It's though about the project, I'm not worried. So I don't know. Yeah. Just I'm new. I'm never really done something like this before, I guess.
well then, I'm glad you're here with us. We are all usually very nice.
Yeah.
If people are
Yeah.
not nice, we throw them out. So that's the rule.
And also, really, it's our job to make sure that you are comfy and you have a great time and that it's easy. And
Yeah. No. That's the
that's,
impression I've
that's our
gotten. You're
job.
both very nice. So it's it'll be good. I'm excited.
Yeah, it's very different from like a regular setting where you have to be scared that people will try to tear you apart when you
Right.
talk.
Yeah. I guess a little
That's
different, yeah, than the
that's what
conferences
we are
we
usually
presented at.
used to. Right. I
That's
don't
true.
know. I think it got better. I think when I started back in time, my masters, like old professors were still out there to get you. But I think people got nicer even in science over time.
I think so too. I mean, now, yeah, you go to a conference and somebody can give quite a poor presentation and nobody tears into them. Instead, they just feel kind of bad. So it's nicer in that way. But I think, yeah,
Yeah.
I don't know, society in general is pretty.
Oh,
It's
yeah.
nice
I
now.
had
Maybe at least the
professors,
people
they would literally tell you, what are you even talking about? Anyways.
sometimes
Yeah.
though, I've needed to hear that in the past. So it's good when people are willing to say that.
Yeah. Well, okay. The time is up. We It was a nice chat. But I think we can start now. So welcome everyone to Science Society. I know that people will still keep coming in, but let me give a short introduction first, and then Victoria will do the rest of the intro in the interview format. Um, and then we'll go from there. So, welcome everyone to Science Society. And of course, a special welcome to you, Lucas, and Dr. Lucas Reinhold Gabert. He is a research associate in mechanical engineering. He did his Bachelor of Science in the New Mexico Institute of Mining and Technology. And then he did his master's degree at the University of Utah and his PhD in robotics at the University of Utah. And it's such an honor having you here. And as I said, I'll hand over the mic to Victoria for the rest of the introduction. Thank you.
All right. Thank you, Katarina. And Lucas, I don't think that we're going to ask you, what are you even talking about? Even if you said that's what people
Okay.
should ask. I think we're going to refuse, right, Katarina? Good. We're in agreement. Great. Okay. We won't ask him. Okay. So thank you for coming. Welcome to Science Society. We are really excited to hear what you have to talk about. This research is really going to be life-changing for people, and I can't wait to hear you describe it and the development of it. And so my question to you is, where do you think your passion for science came from? And that can be answered looking back through your childhood or any time in your life, really, if you can think of when that initial spark struck you.
Yeah. So I think maybe this is slightly different than a lot of folks on Science Society, but I have maybe less a passion for science and more for engineering and for helping folks with disabilities. So my mom is like a high level quadriplegic, so she has a spinal cord injury, and so my whole life I've kind of been around disability. And I actually realized this just a couple months ago, but I had teddy bears as a kid, and I named them Elevator, Lift, and Escalator, which is, I think, not very normal, but just kind of showed from a young age thinking about assistive devices. And so, although I didn't know those terms, but and I always had a fascination for machinery, so like many kids. But and then through high school, I always liked STEM fields. I really liked physics. I find physics very interesting, and then I kind of thought engineering was a good medium between physics and using being able to help people, I guess, but still, what am I? You have the hard STEM ability, but then also the soft skills of helping people. And so engineering is able to bridge that gap specifically in assistive technologies. Although I didn't know all this at the time when I did my undergrad. So I went to engineering, did my undergrad in engineering and mechanical engineering, and then decided to come to a master's at the University of Utah And I was lucky enough to find an advisor here. So that's the person who I did this work that we're talking today under. That's Dr. Tommaso Lenzi, and he has a very nice vision, I think, for assistive devices. And so I guess I'm less interested in the science, because there's also science in assistive devices of like how people move, how can you help them, and like when you help them, how does their body change? What's the biomechanics behind it? And I think I'm less interested in that science and more interested in the technology and how can you design technologies to help assist people. So that's the kind of wavy path to that question.
Yeah, thank you very much. And it's so interesting that you named your teddy bears elevator, lift, and escalator. It really does show. It's like it foretells your future in a way, you know, or just really shows what your interests were. And I get that. We feel here that everything is interrelated. Disciplines of study are not really, they're only separated because of necessity in school, you know, regimentation and being necessary to focus. So what may be wavy to some seems like a very direct path, especially when you explain that you wanted to you're applying the physics to your engineering, and it is all science. So thank you for that description. And so now that's where you are at. You met that advisor, and that's who you're working with on this project right now. Is that what you
Mm-hmm.
had said? Yeah, great. Okay, so then I won't ask you how you got from there to here because you brought us here. So at this point, the stage is yours, and Katarina and I are here to help you field questions. People may put questions in the room chat, and we will look at those and share them with you. You don't have to. And then some guests may come up on stage and ask you questions at the end, like a Q&A. So
Okay.
if there's anything we can help you with beyond that, here we are. So the mic is yours. Thank you so much, Lucas.
Okay, thanks. Yeah, and feel free, I think, to jump in with questions at any time, or kind of point me in a direction if you think that's better. So I'll just start, I guess, with the big picture. So this paper published recently is about a prosthetic knee and ankle, which has power to help people move around. So a little bit of a background on prosthetics in general. Prosthetics have been around for a very long time, and the technology has changed significantly in the last 100 years. So we've gone from knees that are just a hinge joint, basically a door hinge, and so it swings forward when you're walking, but it's not very stable. And then about 50 years ago, researchers started looking at microprocessor-controlled devices. And so these are knees so I'm back up a little bit, I guess. I'm just going to focus on the knee first because it's hard to switch between knee and ankle all the time. So I'm just going to focus on knees for the first little bit. The knees, so about 50 years ago, researchers started coming up with microprocessor knees. And this means that instead of, it's still a hinge, but there's a damper attached, and so you can change how hard it is to push that hinge. And so you can get quite complex with this, and these are still the knees that are in use today. So when you're going downstairs or down a ramp, you can push into it really hard and it supports you as it flexes, whereas a hinge would just buckle immediately under you. And they have quite complex algorithms now. If you stumble, they can help support you when you're walking. They are developed by many different companies, and they're on the market, and they have been for about 50 years. So that's the kind of biggest leap forward in knee technology. There's this just a peg leg, right, 100 years ago. Then you move into hinges, and then these microprocessor controlled knees. And so in this work, what we're trying to do is take that next jump forward, where we go from a microprocessor knee to a knee that can, instead of just being able to resist you, is able to help assist you. So it helps you walk up stairs, it helps you go up ramps, it gives you power when you need it. And we want to enable users to do activities that maybe they could do before their amputation and now they don't do as often. So that kind of brings in the human aspect of this, which is if you have an above knee amputation, it has quite a significant impact on your quality of life. So anything that we can do to help improve that quality of life is good. And a big way to do that is just getting people out and in the community and walking to the grocery store, because if you get an amputation and then you just sit at home, it doesn't speak well for your quality of life. And thus life expectancy, there's many different secondary health concerns that come with that. And most amputations in the United States are due to diabetes. So this is already a population that struggles significantly with walking. So we wanted to design a device that can provide all these benefits that can try to help people walk and go upstairs and ambulate in the world. And this is not a question that is novel to us. Many groups have tried to do this and are still trying to do this, but it's a hard problem because it's just a hard engineering problem. There's a lot of, when you add this motors, batteries, controls, you're adding a lot of weight to the device, and the weight and complexity, really. So you decrease robustness because it's very complex, and then you decrease the ability of people to move around on it because it's heavy. And the weight actually makes a big difference. So you'll notice this is around, the knee in this paper is actually much lighter than the biological leg. And that's something that people are curious about. They say, well, if you make a knee that's the same weight as the biological leg, it should be fine to ambulate on. But you don't have all the connecting structure that you have for a biological leg when your leg is amputated. So it's just kind of hanging there on a socket. And so weight actually matters much more than it does with somebody who doesn't have an amputation. So that's some of the background for the knee joint. The ankle joint is has a similar justification. Microprocessor ankles do exist, although the most popular form of ankle today is just a leaf spring, essentially. So a piece of carbon fiber that flexes when you walk on it. And part of the reason that they're so popular, I think, is twofold. One, it's very lightweight, and when the farther away that weight is from your body, the harder it is to walk with it. So a heavy ankle is harder to walk on than a heavy knee. So adding weight to the ankle is really has a lot of negative effects on walking. And also the ankle is less necessary in many gait tasks than the knee is. So for instance, standing up or going upstairs, the knee provides a lot of power, but the ankle doesn't. But there's still many activities that you can assist with power in the ankle. You can provide better toe clearance. You can provide push-off during walking, make it easier for people to walk. So that's the background on the need for these devices. And powered prostheses have been under development in both knees and ankles for about 20 years. I guess longer if you count tethered systems, which would be systems that are hooked up to a big machine. So you can't take them outside of the lab or go anywhere with them, but that researchers more than 20 years ago started looking at putting somebody on a treadmill and then having a prosthesis that's attached to big motors that's like in a lab where they can't walk more than 5 feet from the machine, but still giving power to them. And yeah, so that brings us to this device here, where we're trying to create a prosthesis that can fit this lightweight design requirement and be robust, and so we can actually design a prosthesis that people can take home and walk easily on because it's light. So we can look, if folks have the paper, I think you posted a Google Drive link to it, Katerina. So
Yep. Yeah, I didn't
we can
want to
see.
overload the link you provided.
Okay, yeah,
You know, that way it's better.
yeah. So thank you for doing that. If we look at figure 1, we can see the design of the knee and ankle. So there's 2 separate modules. There's a knee and an ankle. They can work together. They can work separately. And there's a couple in the design of this. So people have tried for a long time to address this problem, but there's a couple things that we did differently, or kind of the novelty of this device in terms of mechanics is due to 2 main things in the knee and the ankle. So the kind of biggest one that I'll probably spend the most time talking about, because it's, I think, the most impactful outcome, or the contribution of this work, is the torque sensitive joint. And so that's in figure 1. That's at the top of the knee, and this is a joint that we designed. This is primarily my co-author, so Min Tran. He did all the math and simulation and design of this torque sensitive joint, and he spent most of his time on the knee, and I spent most of my time on the ankle. But we contributed to both. They're definitely not separate. And so the torque sensitive joint in the knee is kind of the main contribution that allows it to be this lightweight. And then there's also in the ankle, the main contribution is this underactuated system that connects both the toe and the ankle joint. So I'll just lead you folks through the paper here. I think that makes the most sense. So the way that our design framework works in the lab. So we start with a big picture approach, and this is kind of this design framework is how the director of the lab likes to approach problems. So for most problems that we approach, we use the same framework. You have this big picture problem, which is just, we would like to help amputees, help amputee mobility, and we we think that the best way to do that is to design powered prostheses that are lighter and smaller than prostheses available on the market or any research devices available. And so both we can try and push them on the market and try to sell them to people, but also just having smaller prostheses that work better allows for better research. So it really helps both research and industry. But the design framework is, we start with mathematical simulations of this device. So we just have a simulation that we run in MATLAB, which is a kind of programming language for scientists and engineers that some of you may be familiar with. If you, I don't know, who exactly is listening, but it's essentially a programming language. It's nice for simulations, and we make a kinematic model of the device, which means we basically say, here's the motor, and then these are the dimensions of the device, or what the dimensions it could fit inside of. And we kind of want the design to be this certain way. So this is a slider crank mechanism, which maybe is a technical engineering term, but basically it means we have a ball screw trying to think of exactly how to explain this. Well, it's a slider crank mechanism, and I guess the details of that, if you are curious about the exact details, let me know in the chat, but I don't know how far into that I should go. So we have this design framework, we put in the kinematics of the device, and we simulate several, hundreds of millions of designs within this space, using this design framework, and we come up with the top designs that seem to have the lowest force on all of the components, so they're the most robust, and they have the highest or the lowest requirements of the motor. So you're not overheating the motor, you're not pulling too much current from the battery. And so if we look at figure 2, this shows the results of this design framework for the design we selected. You can see figure 2A shows for walking and stair ascent what the torque and speed at the joint level is. So this is the way we do this simulation is we take biomechanical data just from people walking, and we people walking, people going upstairs, people doing sit to stand, so different activities, and we put these inputs of the torque and speed at their joint into this framework. So we say, if we design our device to provide this same torque and this same speed, then what's the requirements of voltage and what's the current requirements at the motor? And so you can see that in figure 2C. We have max voltage and then current RMS. And so this shows that in these simulations, with this torque adaptive, torque sensitive joint at the knee that I mentioned earlier, we're able to do both walking and stair ascent tasks within the simulation framework, whereas without the torque sensitive joint, we're not able to do both of those tasks. So through this design, we settled on through this simulation framework, we settled on this design that allows us, that kind of is at the limit of the smallest components and the smallest motor we can find, the lightest bearings, etc., but still allows us to perform the tasks that we want to perform. And so let's see. Oh, I didn't post the supplementary materials. I think I might skip a little bit ahead to figure 7. So we'll just talk about the knee design. This is a little bit more in depth. So, and what we're just going to focus on here is this torque sensitive actuator, and that's mostly shown by figure 7B. So this torque sensitive actuator is kind of the secret sauce behind this knee. And what it does is, if you're familiar with a torque, so you have some torque at the knee joint, that's what you're trying to provide, and torque is a force times a distance. And so if you're 1 meter away from some joint and you push on that, try to rotate that joint at 1 meter away with 1 Newton of force, that's 1 Newton meter. And so the way that this torque sensitive joint works is it, when you try to ask for some force, then there is a spring, there's a mechanism, this torque sensitive joint gives you a higher moment arm for that, to try to provide that force. So let's say you have the knee. This is kind of difficult to do without being able to use my hands, so sorry for moving around on this, but when you have some force, if the knee is asking, let's say, for 10 Newton meters, it's pulling down on this mechanism here. So figure 7B, there's this spring actuated joint. And that's where your motor is pulling. So it's pulling on this thing in a slot, on this joint within a slot. And when you pull on that, you create a torque around the knee. And so when the motor when you ask for a torque at the knee, you pull on that joint. If you pull harder, you extend the spring more and your moment arm increases. So through that mechanism, the torque at the joint, your torque ratio or your transmission ratio increases when you ask for more torque. And so this just allows us to perform both tasks that require high speed and low torque and tasks that require high torque and low speed. Is this torque sensitive joint. So if we go back to the results, to figure 2, you can see that in walking, you have lower or higher speed requirements. This is figure 2A. You have high speed requirements. You can see that in the second plot, and you have low torque requirements in walking. So we can perform both that activity, because when you're not asking for a lot of torque, you don't get a high reduction ratio. And then in stair ascent, we're asking for low speeds but high torques, and you can do that as well, because when you ask for high torques, you get a higher reduction ratio at the motor. And that's shown by the second part of that of figure 2, which shows that in walking, the torque ratio, in stairs, the torque ratio increases during this high torque activity. It also increases in walking during stance, which is fine because that's the low speed part of walking. So anyway, that's kind of a lot on that torque sensitive actuator, but that's the meat of what makes the knee different. And so then there's figure 3, which is a characterization of the knee. And this kind of figure is in the paper mostly to show the performance. It's kind of an engineering specific figure that just shows, with some standard metrics for the engineering community, here's how well the knee performs. So this provides some reference for other devices. So if you want to look at the impedance of the device, for instance, and compare it with the impedance of a device somebody else publishes, you can use this figure. And so this isn't necessarily important, I think, to understand the knee itself, but mostly to make comparisons with other devices. And same thing with the ankle as well. And actually, so for the ankle, the contribution of that is this underactuated mechanism that connects the toe joint to the ankle joint. So there's if we look at figure 8A, that shows the kinematic diagram, and essentially what this mechanism does is when you're walking, you flex your toes in late stance. So you walk, you roll over your foot, and when you're pushing off, your toes flex. And we use this flexion of the toe to actually provide assistance to the ankle joint. That's essentially what this does. And so by using this toe flexion, we can reduce the requirements on the motor, and we can get away with a smaller device with smaller batteries because we have less power output from the motor and less power requirements at the motor. And so using, so that's the design of the knee and ankle, and then we take these two mechanisms that themselves are they're novel mechanisms. Of course, they build on other things within the field. So, like for instance, torque sensitive joints are not. This isn't the first torque sensitive joint ever made by any means, but it's the first one put in a knee prosthesis. And with these kind of design ideas and design parameters. And so from that, then we can use these two devices now to do all sorts of activities. And so that brings us to figure 6, which just shows a bunch of different activities performed, and I guess figure 5. So we had some subjects, we had 3 subjects come. These are folks with above knee amputations, and they walked on both the knee and ankle together, and we had them perform a bunch of tasks. And so we can see figure 6 is just a big matrix of plots, essentially. It shows knee angle, knee torque, ankle angle, ankle torque, and same with the toe. And we can see that with using this device, we are able to get similar profiles in walking, in stair descent and stair ascent that that able-bodied people get. So this is promising. It's not a comprehensive clinical trial or anything, but this is a promising result that by using this device, people can get restored gait that's a mobility level that's more similar to what they had before the amputation than what they can get with passive prostheses. Yeah, so that's let's see, that's the human trials. And so kind of moving away from the paper a little bit now. So this paper explains the device, how the device was designed, what the performance of the device is, and I really enjoyed working on that, and I think it's very nice. But what I'm really excited about is the things that this device enables. So now, because we have this knee and this ankle that matches the weight of microprocessor devices, so these are devices that people have that they're used to the weight of. It matches the weight and size of those, so it's very easy now to do trials where we try and push these devices, develop control algorithms for them, and get some real data on how these devices can help people, because we don't know. So this field is has been around for about 20 years now, but there's been no study that's shown that a powered knee prosthesis actually helps people walk. And that's due to primarily, I think, to no prostheses having the ability to help people walk yet. So we're hoping with this device that we've kind of overcome that barrier, and now we can start providing this data and adding to the body of knowledge about what powered prostheses can actually do. So we actually we have a grant to take these devices and send them home with amputees for 3 weeks. So I'm really excited about that. And that's part of why this design we worked really hard on a lot of aspects of the design. To all the wires are concealed, there's no pinch points, it's very robust, and part of the reason for that is so that we can send it home with people for 3 weeks and measure their how many steps they take, measure different metrics of their ambulation ability, and use that to determine, does this device actually help somebody in the real world or not. So that's I guess 30-minute overview of this paper. I don't think I hit everything, but it's hard to hit everything in 30 minutes. Yeah, any questions, discussion points?
Yeah, thank you so much for giving us this overview of the work and the development and the analysis like you did beforehand, the modeling and prediction. It's really interesting to learn about that and um, which components were important to have less strain on battery and so on. I don't think I thought about this before, and it's really beautiful that the Slack basically gives additional strength um, to the user. Um, it's that is really exciting. And since you started talking about the clinical trials, did you see just by using this leg that there's some recovery process going on? But because I don't know if you know Miguel Nicolili's work with exoskeleton during the World Soccer World Cup, where they kicked
No.
basically the ball, and there was very surprisingly a recovery going on for paralyzed people by using those legs,
Oh.
but they had sensors that kind of gave a feedback into the arm, for example, or to
Hmm.
a place where they still had sensory input. So yeah, I don't
Yeah.
know.
That's a good question. This we haven't seen any recovery, but that's a hard thing I think for amputees to have. There is a lot to be said for keeping muscles strong, and so by using this device, for instance, I guess I maybe didn't highlight the downsides of the devices people use currently enough. But so with passive devices, with these microprocessor devices that exist on the market, uh, you can't get any power with the device. So if you put your weight into it, if you're walking upstairs, for instance, and you put your prosthesis on the step in front of you and you try to go up it, it doesn't give you any power. So people don't do that. So there's a lot of activities that people just don't do with that leg because the knee isn't there to provide power. And so with this device, the knee can provide power. And so we hope that because the knee has power, people can use this uh, device to strengthen their leg and have muscles activated that aren't activated with their regular with their prescribed prosthesis or with prostheses that have been available uh, previously. So we're hopeful that is the case, and we haven't yet uh, finished any studies looking at um, muscle strength in the leg. So I'm not sure what the outcome of that would be.
Yeah, that's really interesting. And yeah, I guess this case is very different. Do you have maybe also patients that have chronic pain issues? And I don't know, but I could imagine that by kind of distracting the neurons to do stuff again, uh, that maybe chronic pain issues could go down, but it's maybe too far-fetched, but would be nice. I know that Miguel Nicolidis, it took like over a year to see those effects. Um,
Yeah,
so I don't know
yeah.
how long that would take.
Chronic pain is a uh, difficult nut to crack. Or you're talking about like phantom limb pain? Is that correct? Where if somebody has an amputation, they still feel pain in the limb or part of their body that was amputated?
Yeah, exactly. For example, or
Yeah.
also then, yeah, there's also a lot of chronic pain additionally elicited due to prostheses that don't fit exactly well and kind of irritate on top. I think that's a
Yeah.
very contributor.
Yeah. So for prosthesis fit, there's having a lightweight device helps, because if you have a really heavy device and you have to that's pulling on your socket all the time, then it can exacerbate any issues that you have with the fit of the device on your leg. So lightweight helps with that. And for chronic for phantom limb pain, it's not necessarily my area of study, but there is some interesting work being done on reinnervating the nerves that lead to the affected area. And so you can hook those up to a prosthesis and you can get some feedback from them. So Jake George, for instance, and several other research groups are looking at this. And you can actually get some connect those nerves up to signals in the prosthesis, and that shows some promise in helping reduce this pain, because you're giving those nerves a function again, instead of having them just hang out in the end of a limb and not really being connected to any sensory inputs.
I'll ask one more question, and then I'll let Dennis came up to the stage, and Joyce, we are trying to bring you up if you're listening, but it's not working. So maybe if you would restart the app, then it will work. So because you told us, about your story and your mother, would it be a big deal? Probably it is, to turn this into an exoskeleton to help paralyzed people moving well, because I thought maybe the requirements, to have the joints characteristics you designed with your colleagues, that maybe they would also be very helpful for some type of exoskeleton device.
Yeah, that's it. It does take a lot of work, but that's a good point, and that's actually something we're working on right now. So somebody else in the lab, Brendan, is. So I'm still in the lab that developed this. I graduated, but I stayed on as a research scientist. And Brendan is taking this same torque sensitive actuator design that I talked about for the knee and using it for a knee exoskeleton. So we do think it shows promise there, because it is a solution that's lightweight and small, and that matters a lot also for exoskeletons. So there are exoskeletons that exist for spinal cord injury that are quite large and heavy and not. I mean, it's a hard problem, but not necessarily easy to walk with. And so we think that if we can make the actuator smaller and lighter, that will help the problem. Yeah, so it is applicable. And to more also than just spinal cord injuries, there's if you can, there are many health conditions such as stroke or brain injury where part of your body function is affected. So you still have the limb, but you just can't use it very well. And we think that exoskeletons could be a promising solution to address that. So help people with stroke, for instance, walk faster, and thus be able to go around the community easier and stay home less.
Yeah, that's wonderful. And do you know if for guiding basically, or controlling the exoskeleton, if they're using brainwave activity, like through a helmet, basically signaling?
Yeah,
Oh, that's great.
we aren't looking at that. There are some groups who are interested in that, but I think that's still very far away. So, like EEG, these helmets that look at your brain waves, can be. It's not a very well known science yet, so there's still a lot of one common approach to that is to take the information that you get from this sensor about the brainwaves, kind of feed it into some machine learning algorithm, essentially, and you get out with some information about what parts of the brain do what, and you get out what the person wants to do. And to really control an exoskeleton and be able to assist somebody, you need something that's a little more more consistent, more reliable. And one of those options is electromyography, EMG, which is, it doesn't look at the brain waves, but if you flex your muscle, any muscle in your body, there's some voltage that's created on the skin from the activation of that muscle. And you can actually read that voltage that's created on the skin and sense that the person is activating their muscle. And you can use that with exoskeletons. That's a really nice tool. So if they have some ability to flex, so for instance, with somebody who survived a stroke, if they have some ability to flex a muscle on their leg, you can hook up this sensor to that muscle. And then when they flex that, you can have the exoskeleton assist them. So you can make up for all the other muscles that aren't working, or the muscles that aren't working to their full capacity. So that's a really nice control avenue for exoskeletons.
That's really great. And it also should be, if I'm still up to date on that type of research, interestingly, the individual characteristic of each person, how people switch the muscle, like how the signaling is very different from person to person. So it would be additionally kind of a security, cyber security.
So,
Maybe. I don't know if I'm still up to date, but I read that, people wanted to use that signaling instead of like EEGs, and to, let's see, to analyze, for example, how stressed people are, or, other different type of states, like body states. And they couldn't, because each individual has such a variety of signals, characteristic ones, that the noise is just too big to like discern groups, basically. So would be interesting if that could be additionally also a security thing. So
yeah, I mean that is security on one hand, but on the other hand, it's nice from a translational perspective. Uh, if your device works on everybody very easily, then you need less clinical time to get it set up. You need less personalization, and then that means everything's cheaper, right? Because healthcare, at least in the United States, is very expensive. So that's something we push for on the prosthetic sides of things, especially for things that we think are close to translation, is we try really hard only to design control algorithms that are easily translatable from person to person. Because if it takes an hour to get this device set up on somebody and make it work, then because you have to personalize everything and tune it just for them, then that makes it really hard to make that useful in the real world. So
yeah, I mean, you could probably at home with an AI, type of thing, train it yourself maybe. But that's true, and that's why I have more hope for engineering solutions than organic solutions to like regrow stuff, body parts, and even organs, because that's we didn't figure out how to make cells that you can put into everyone yet. Like, we would just reject them. But artificial hearts
right,
are working pretty well, without having to take heavy medications. So hopefully, the engineering world, if I would put money on it, I would I would put all the money into that research, like artificial kidneys, not from cells, from whatever
Yeah,
engineering materials you would need probably, and then replace them like a pacemaker once in a while. But yeah, I'm not sure if we can ever solve the immune response issue to make it cheap enough that you can scale it for everyone off the shelf. I don't think organic will work, but
yeah. I mean, hopefully one day. I mean, yeah, that's something that is nowhere near being close, and also not my field of research. But yeah, regrowing a limb or something would be very nice if it worked. But I agree that it's not close.
yeah. So yeah, sorry for taking over a little bit here, but Denise and Kirko, please go ahead with your questions. And Victoria, if you have more questions, please go ahead too. Thank you.
Kirko, you want to go first?
Sure. So I can't lie, I not my field, but super cool. But I was kind of curious, like, about these two things. One, is it possible? Because like I saw there's like some electrical components to the limb, or the prosthetic. And I was kind of curious, is it possible? Because like when you walk, that motion is moving the stuff on the torque side. Is it possible, kind of like how some like electric cars kind of can recharge off of the torque created from like the brakes or something like that? I can't remember exactly how it works. But I was kind
Yeah,
of curious if it's possible that that motion of walking and stairs and so on and so forth can help charge the electrical components of the prosthetic.
yeah, that's a great question, and that's actually something that we showed in the first time for this paper. So that is possible, and you can, if you basically turn the motors to just resist movement really hard. It's the same thing as braking in an electric car. It's you have the exact right analogy there, or I mean, not even analogy. It's the same mechanism. You can, if you walk on the knee and we set the knee to just brake the whole time and not give you any power, then you do actually recharge the batteries. And there's a whole supplemental materials paper that goes along with this that I don't know an easy way to get access to right now. Because I think the link that I sent only shows this. But this leg is able to do that, and that's something that you need. Uh, One, it's really good for amputees because if you have a device that only works when it's powered, when there's a charge in the battery, uh, and it's possible for the battery to deplete all the way, and then you have to find an outlet somewhere to recharge it. That's a frustrating thing. So by using this mode, it's possible to basically just have the device break all the time. So it's much harder to walk. It doesn't assist you anymore, but you can still walk around with it. But yeah, it can do that.
Super cool. I have like one more question though.
Yeah.
So, how do I state this? What it kind of seems like when you were talking about how you can go like I think it was like high torque, low speed, and then vice versa, and that kind of
Hmm.
can help dictate like the speed of which a person can move, or the amount of force they can put down, like walking upstairs, something like that. I'm trying to understand in
Hmm.
my own language. But
Yeah.
I was kind of curious that if you can kind of get that type of control as you go through like the programming on how things change depending on the motion and so on and so forth, if it's possible to like be able to like I guess like like I'm thinking sports wise, right? You have to be able to like stop, start, put different amounts of pressure on the inside, outside, front, and back of your foot
Hmm.
to be able to do certain movements. Is it possible that something like that could be like programmed in? Because it almost seems like this could be like part of like a new way to for um like Special Olympics type sports for like people with disabilities like missing limbs. You have like sprinting, of course, already, but
You're
you know what I'm
you're
saying?
saying like using this leg more for sports or for like extreme activities rather than just getting going up some stairs.
Yeah,
Is
like
that?
because I don't know, man. Like it kind of seems like there's a definite application from how I'm understanding, like maybe not so now, but as you can continue to make advancements upon how the actual prosthetic works, that's
Yeah,
like a definite avenue.
yeah, I think that's a really exciting avenue for it. And the thing that the field is waiting on for that, I think more. I think these mechanics can handle it, especially in the knee. I mean, I'm talking mostly about the knee because uh, it has a bigger impact, I think, in folks' quality of life than the ankle does. But with the knee, and I think it's a little farther. It's closer to being translatable to a real product than the ankle is. I think the ankle still has some steps, but so I think the knee is pretty close. The mechanics, but the hard part left for that is controls. So if you're talking start stop, you're talking these, there's the like football exercise where you step through the tires. I don't know what that's called, but some activity like that, which this leg could give you the ability to do. We still don't have the ability to control the leg to make it do that. So there's a lot of different avenues, and that's kind of what several folks in our lab are working on, as well as these different avenues of how do you get the leg to do what the user wants instead of just what's programmed in as like walk, stairs up, stairs down, go up ramps, go down ramps, these kind of set activities. If you want to do some crazy movement with your leg or like a karate kick, currently they can't do that. And so one promising method for that, I think, is EMG control. So what I talked about again, where you can measure muscle movement, or like if somebody's flexing their muscles, you can put those sensors on the person who's using the prosthesis, like in their socket on the residual limb, and you can get a lot of information from that. So hopefully, in the future, we can see cool sports activities like that. But also from a science standpoint and from a clinical standpoint, we spend some energy on that, but the focus of it is just on helping people get up off the couch, because that's really where the quality of life impacts come in. I think more if you're a young, strong amputee, you can do a lot of these activities, but it's the folks who have diabetes, they're older, don't walk around much, that really see these negative impacts after an amputation. And so we're trying on the clinical side to address those.
Legit. Thanks for asking my questions.
Yeah.
Hi, Lucas. Thanks for this really interesting talk. I had a couple of questions. The exoskeleton one was asked, so I was curious, what is the weight of these units? And you had mentioned that so far they're still tethered. What would it take to, and how much energy usage is there, and what would it take to untether them?
Okay. Yeah. Sorry. I think the tethering, I was unclear. That was like 20 years ago when people first started developing these devices. So the device that's shown in this paper is fully untethered. You don't need a laptop or anything. It can just ambulate on its own. So it has all the batteries, controls, electronics, everything is inside the device. And sorry, I forgot the first part of your question.
It was about the energy usage. So now that they
Yeah.
are fully self-contained, what's the operational time?
Yeah. So with these devices, you get maybe half a day on them with the batteries that we have. And that's actually kind of independent of how much you walk on it, because for these specific devices, a lot of the energy just goes to the electronics, because we didn't take time to really fine tune all the electronics. The motor driver has pretty high power requirements even when you're not driving the motor.
It's always on a hot standby, basically.
Exactly, yeah. And so you don't get very much. But if you take this same design and but even with that, I think we estimate we didn't actually have somebody walk on it this long, but something like 10,000 steps. And in this battery recharging mode that I mentioned earlier, you can walk indefinitely, right? Because then you're not consuming the battery because you're actually recharging it enough to that you're not lowering the battery voltage over time if you are walking on it. And that those plots are shown in the supplemental materials, which I should have provided a link to. But if you have a way to get that, whatever way is, however you can get your hands on it, you can see the plots where the battery voltage goes up. But I think even if you just take this device right now, how it is, in terms of physical mechanics, you just improve the electronics, you could get a day of walking, and so I think it would be possible to sell it as a device, and then people just have to plug it in overnight, every night, and then that's the case. And I guess, on that kind of topic of more usability of the device, we're working. So we just signed a partnership with Autobach. They licensed this torque sensitive joint, and we're working with them. They're the largest prosthetics manufacturer in the world. They're based out of Germany. We're working with them to take this device and translate it into a device that can be sold on the market. So we're hopeful. It's very hard to predict the timeline on these things, but a couple years till we can see this device out there.
Nice. Are you getting interest from exoskeleton vendors or other actors?
Yes. Well, in that, I guess Autobach is also designing exoskeletons, and so we don't have anything nearly as formal with them in terms of taking this device and bringing it to market for the exoskeleton side of things. But we're trying to work on seeing what possibilities there are in terms of commercialization of the technology on the exoskeleton side.
What do you think is a time frame for commercialization of exoskeletons? I understand that they're they're
Yeah,
being actually tell me whatever you can.
yeah, I think that's a hard question. So I'm a bit of a technology pessimist, maybe, in that I I need to be convinced that a technology provides really a lot of help to somebody for them to want to include it in their lives, right? Because charging another device and having that like mental labor of, oh my, is it acting weird? Is it not? Takes a lot from somebody. So for exoskeletons, I don't see, there are companies right now selling them. You can go, Robotic sells one that, makes it, reduces loading on your knee when you're skiing, unless they discontinued or changed their approach on that. But I haven't seen a really clear path forward in the exoskeleton department for devices that you take home with you and you wear every day. And I think that just comes down, in my mind, again, to size and weight and difficulty. So if it's something that's really easy to do, people will be more likely to include it in their lives. But it's not at the point where prostheses are, in terms of benefit to cost in a person's life. Yeah, I think there's still a lot of science to be done and a lot of questions to be answered about what are the areas in which people need to be helped with exoskeletons, and then we can focus on addressing those areas.
Yeah, find the need first, then design the solution.
Yeah.
Right on. Thanks, Lucas.
Mm-hmm. Thank you.
Yeah, thank you so much for answering all these questions. I really like the point you made that I think we are only transitioning now very slowly to really asking people what they actually need improved in their lives. I think a lot of stuff used to be designed by people that have nothing to do with the problem. They just imagine that this is what people should need. I don't know if you realize that, but
Yeah, I
yeah.
think it's common in engineering because engineering is fun to kind of find a solution. You have a solution that you like, and then try and find a problem for it. And that doesn't lead to good results or things that are applicable, um, or that help people in the real world. But yeah, I think the field is moving away from that.
Yeah, and I think it's really, yeah, I think that's a really positive transition, and I'm really looking forward to the future, where people's needs are met, and using all the technology development we have to help people have a better quality of life. So congratulations for doing this work and developing these. I think it will help a lot of people, and I hope it goes fast, to have these legs on the market, and yeah, developing many more very useful, cool tools. So do you think, yeah, that the military, I think Kirko's question, I was thinking also about that. That's maybe my last question, that you could enhance people's abilities quite a lot, or you could use this technology also to improve robots. Is there anything also going on in that direction in your lab to, just improve how legs work in robots, and how they move? And because I guess by the usage, just from the usage of your robotic legs, that data could maybe be a training data for robots to walk well in different types of surfaces, and agility, I guess.
Yeah, that's a good question. The field right now uh, is relatively separate. So in terms of humanoid robotics or robotics, something like Boston Dynamics or Agility Robotics, their robots versus us, don't really know. I guess I don't know. The fields are relatively separate. So I think that there are things from this design and from prosthetics that could be applied to help humanoid robots, and I'm probably some other things that could translate the other way as well. But I don't know enough about that field to say what I think exactly from this design. I mean, I think the torque sensitive actuator, I guess, could be useful in humanoid robots to get higher torque with a smaller design. But in terms of controls and data sets, yeah, it's hard. I don't know what would help them come up with better designs or have devices walk smoother.
Well, I'm telling you why I had right away almost that idea when I read your paper, when we had a lot of time on our hands here on Clubhouse, and we used to talk for a whole day sometimes. We came up with what would be the best way to make us basically immortal. The best way would actually be to just keep the brain young. The rest is kind of a waste of resources, right? So you could have all this immortal brain stored in a very safe place away from radiation and everything, and just have those humanoid robots walk around for you and give you
Yeah,
all the input, and travel through space wherever.
it's true. I mean, you don't have any oxygen requirements for this. So if you want to go to space, with your robot body. This could be a good leg. This could be a promising leg to use for that.
Perfect. So we have a leg.
Yeah,
Now we just have to
we'll
figure
work
out
on
how to, it kind of Futurama type of way. Just you sit in a
it. Yeah,
glass, but you have your robot walk around for you, I think. Yeah, the rest of the body is kind of a waste, to keep that alive.
But you couldn't
yeah.
eat chocolate, could you?
Well, the robot
Oh,
could, and if the sensors are good enough, it gives you the same kick, hopefully.
Okay.
So yeah. Well, there's
yeah.
a
I'll do
lot we
percent.
have to solve, but anyways, we have the legs.
Yeah,
Well, there's still Clubhouse. We can goof around a little bit. Yeah, unless anyone else has a last question. Does anyone please, signal? If not, we'll close the room. Lucas, it was such a pleasure having you here. This is really exciting work for many reasons, but especially for the reason to help people improve their quality of life. So congratulations, and I hope we'll keep following the work, and I hope a lot of funding and a lot of people helping will lead to more progress. So we are curious. It's always hopeful to have these rooms to be hopeful about the future. So thank you.
yeah. And thank you for the invitation. I appreciate it.
Great. And thanks everyone for coming and asking questions and commenting. It's always way more fun and better discussion if people participate live. And if you like discussions like this, we'll have the next room later in the week. And the researchers did reanalyze DNA from 18th century African descendants and discovered new like revealed new origins and new information. So I think that will be really, it's a very different type of research, but it will be also really interesting. So thank you, Lucas. Thank you everyone for coming, and I'm closing the room in 3, 2, 1. Bye everyone. Thank you.